Sorry. So I was saying the Chandra X-ray Observatory is one of NASA's great observatories to look at the universe, and it looks at the universe in the X-ray band. Hubble looks at the universe in the visual band, and Spitzer in the infrared band. And I've been, as Ramesh said, I've been associated with Chandra since before launch. And I was there at launch, and here on the left you see an image of the shuttle, NASA shuttle Columbia. It was launched on the 23rd of July 1999 with Chandra on board. And Chandra is the largest satellite ever launched with a shuttle, is 14 meters head to toe. This is the shuttle bay, and this is Chandra being deployed in orbit and the Earth in the background. Here's a diagram of Chandra. This is where the photons come in, the X-ray radiation from the universe, and this is the mirror, which is 1.5 meters across. And here's the focal plane, 14 meters, where there are two instruments. There are two imagers. One of them has energy resolution, and there are also two gratings assembly that can be put in front of the beam to get dispersed spectra for better resolution. Here is the aspect camera, which is an instrument, is a CCD that looks at the sky and gets pictures of stars in the visual light. And you can compare that with the known position of these stars, and this gives you a very accurate position of the X-ray sources. And these two are thermal panels that look at the sun, and they get radiation from the sun that generate the energy for Chandra. And it is interesting that the electrical power that's needed to operate Chandra is 2 kilowatt, which is the same power as you need for your hair dryer when you dry your hair. So it's impressively little. Okay, this is another diagram of Chandra that shows the path of the X-ray photons. And to reflect X-ray photons and make an image, you need to go at very shallow angles. And it's like skimming a pebble skimming a pond. And so that's why Chandra is so long. And here is the focal plane. It's one of the instruments, and the photons build up an X-ray, an image of the certain region of the sky in X-rays. And we register each photon individually. We know from where it came from, we know the energy, and we know the time of arrival. So we can do a lot of different studies with these data. Now, why is Chandra special? And the reason it's mirrors. It has the best resolution ever seen for an instrument to look at the sky in X-rays. And here are two images of the mirror being polished, one of the shells being polished, the mirror being assembled. There are two sets of 4 shells, concentric shells, and we had to prove to the United States Congress that the mirror was so good before launch, because otherwise they wouldn't give us the money to carry on the mission, and that was successful. And to give you an idea of the resolving power of Chandra, which for astronomers is basically 0.3 arc seconds, but what it means in reality is that it's equivalent to be able to read a street sign, like a stop sign, at a distance of 20 kilometers. So it's pretty good. Here I'm giving you an example. This is an image of the sky, the Orion Nebula, where there are lots of new stars being formed, as observed with the Rosat satellite, which was the previous mission, the previous best mission in terms of creating an imaging on the sky in the X-rays before Chandra. And as you see here, there is a very crowded regions where there are lots of stars being formed, but you cannot see the individual stars. You see some of them on larger radii where there is less crowding. With Chandra, same region of the sky, this is what you see. So you see lots and lots of individual faint stars all over the place. You can study them individually. There is lots of science that can be done with Chandra. An example that comes from Earth observing, just to give you an idea what the increase in resolution can give you. This is an image of the airport of San Francisco seen by an Earth-looking satellite with the same resolution as ROSAT, the mission we had before Chandra. And you can see that there are some straight lines, there are some round features, so you can guess that this is a man-made creation of some sort, but you don't quite know what you're looking at. If you look with Chandra, and you look, for example, at this small region over here, this is what you see. You see a plane. So you know you're looking at an airport. So this tells you that, you know, it is absolutely true in astronomy also. Lots of outstanding questions. We take a picture with Chandra and we know what it is. So we have solved lots of controversies just by looking. So why do we need a satellite? Why can't we put Chandra on top of a mountain like we do for optical observatories? And the reason is shown in this. If you look at the radio waves, you can just put a telescope anywhere. But in X-rays, the X-rays don't make it to the Earth, which is a very good thing because otherwise we wouldn't be here. It would be a different world. So to look at the sky in the X-rays, we have to go above the Earth atmosphere. And that's why Chandra has to be a satellite. In fact, what I'm showing here is unfortunately, you can't quite see it. It needs to be darker. But anyway, the orbit of Chandra, this is the Earth. These are the radiation belt around the Earth, and this is the Moon. And this is Chandra. And the orbit of Chandra is elliptical and reaches to 1/3 of the distance from the Earth to the Moon. And if you want to have some numbers, the apogees, so the place which is farther away from the surface of the Earth, is 133,000 kilometers high. The place where the orbit is closest approach with the Earth is 16,000 kilometers. And one orbit lasts a bit over 64 hours. And of these 64 hours, most of the time is spent above the radiation belt. And this is all good time for observing and getting good data. So it's a very efficient telescope from that point of view. This is the rainbow. The rainbow you're familiar with in the visible light. It goes from red to violet. But there is radiation from the universe that comes on the radio wave on one side and the gamma rays to the other side. And you could make a comparison between the X-rays, which is what we observe with Chandra, and the visible light. And in a way, it's the same as comparing a man with an ant, because the energies in X-rays are 1,000 times, each photon is 1,000 times more energetic than a photon in visible light, and conversely, the wavelength would be 1,000 times smaller. What do we see in X-rays? We see hot, violent universe. We see sources that are 1 to 10 million degrees hot. And so we see explosions. We see what comes out of supernovae. We see matter that falls into deep gravitational wells, neutron stars, black holes. You've seen some of this discussion earlier in this conference. And also large dark matter structures that can trap a huge amount of hot gas in equilibrium. We see that in clusters of galaxies. And you also see very fast particles moving near the speed of light in magnetic field. And by and large, Chandra and the X-ray regime gives us a very direct view of the power of gravity. That's the source of all this excitement. Now, why Chandra? Before launch, the satellite was called AXAF, the Advanced X-ray Astronomy Facility. After launch, when everything was fine, the satellite worked, NASA decided we needed to have a better name. And so they had a panel, and they asked for people to come up with proposal. And the winning proposal was to name the satellite Chandra after Chandrasekhar. And here is an image of Chandrasekhar, and this is an image of Mrs. Chandrasekhar with the winners of this competition and the model of the satellite. And there is a very good reason for that, and the reason is because neutron stars and black holes, which were very much part of the scientific legacy of Chandrasekhar, are very prominent in the X-ray sky. Now, what I'm going to do now is to give you some highlights of what Chandra has revealed to us. And I'm going from the nearby to the far away, from the smaller to the larger. So I'm starting with stars. And Oops. No way. Cancel. Okay, so this is a cartoon of stellar evolution. What we have, say, in the galaxy, there are clouds. And these clouds, if they're big enough, they're dense enough, they will collapse, and they will, because of the gravity, and then will form a star. So this is what happens. Gravity makes this stuff collapse. When this material has collapsed enough, it will get to the point when it's dense enough to start nuclear reactions. And at that point, you have a star. You have a star, for example, like the sun. This is an image of the sun, in fact, as you see it in the X-ray band. And what keeps the sun alive is at this point, our sun is using hydrogen to make helium. And this produces energy and stops the collapse. There are many stars like this. Stars can have the mass of the sun. They can be 100 times more massive. And with Chandra, we can see regions in which this star form. For example, this is a region of star formation. This is the original mother cloud, seen in the infrared with Spitzer, the infrared great telescope of NASA. And each other blue dot is a star seen with Chandra. And the point I want to make you is that if you look at this with an optical telescope, all you see is black, because the dust in this cloud will absorb everything. So you cannot study these very young stars. You can with Chandra. You look here, you can see them individually, and you really can follow up what's going on with them. Now, so a star, as I said, is kept together, is kept there because of equilibrium between gravity that wants to shrink it and the energy from fusion that keeps it where it is. What happens where all the material is being converted in iron, which is the end product of this process? Well, there is no energy to counterbalance gravity, so the star collapses. And the end of this collapse can be a white dwarf. And this is important from the Chandrasekhar point of view, because Chandrasekhar, when he was 19, on his way from India to England for his fellowship, realized that there is a limit of mass to this type of end product. If a star has to be less massive than 1.5 times roughly our own sun to end up into a white dwarf. A white dwarf is something that, our sun will become a white dwarf, which means it will shrink to 100 times its present radius, will be as big as the Earth. And the white dwarf is being kept there by a different balance. These is the electrons in the star that get compressed together up to a point where they really their quantum state won't allow them to be any more compressed. And so the electron pressure, degenerative pressure, will balance gravity. However, this happens only if the star is less than 1.5 the mass of our own sun. If the star is more massive, up to 3 to 4 solar masses, gravity wins. And the star will keep shrinking till the neutron pressure will come in. And that will stop the star, which then becomes a neutron star. When that happens, this is a very fast happening. This collapse, you get the neutron star creation. You also get the outer layer of the stars, the original stars, being kicked out by a supernova explosion. However, if the star is even more massive, you can't see anything here, you get a black hole. Okay, so that's very simple summary. What I'm showing here is these are Chandra images, Chandra satellite images of Cassiopeia A, which is a supernova that was, the star was seen going off about 330 years ago. It's a distance of 10,000 light years from us. And this is the X-ray image. And I'm showing you a little movie. We'll show you 4 images taken different years. And then it will show a superimposition of this that shows the expansion of this shell. So you will really see the supernova expanding. Also, different colors show different energies and different materials that are coming from the original star. Like this jet is silicon. This red here is iron from the core of the original star. Okay, let's start the movie. Yeah, so these are the various images. And the place to look at is this faint outer shell. And yeah, you see it pulsating. All right? And that basically, what it does is expands out, and these images are superimposed. So this is quite interesting because we can directly see this supernova expanding because of the resolution of our satellite. And this is also a model of what happens in the supernova, and it really shows that we're not dealing with a symmetric explosion. Clearly, the original explosion wasn't as simple as the models would make it be, which is not so strange in nature. With Chandra, we also see the neutron star that was left over, the compact remnant. This is just an artist's impression, but we do see this dot of light, X-ray light, at the center of the expanding shell. I'll give you another example of supernova and of neutron star. This is the Crab Nebula. And in blue, you see all the X-ray stuff. And I will show you a little movie that shows what this may be. Here it is. And basically, you have a pulsar, it's a neutron star, rotates very fast as magnetic fields and creates jets of accelerated electrons and particles that are emitted from these stars. Here is another image, which unfortunately, if you could see the original, would be much more impressive. It looks like a hand, a cosmic hand. And so this is the pulsar, and then you see a wind coming out of this pulsar of accelerated particles that hits a cloud in the galaxy and warms it up, this cloud, because of shocks, to X-ray temperature. So it's a fairly spectacular image of the X-ray sky. There is another configuration in which we see neutron stars or black holes, and this is, as Ramesh was talking about this morning, if they're in a binary situation. So in this case, you have X-ray sources that can be 1,000 to 100,000 times more luminous than our own sun in X-rays, and we see that these sources in our own galaxy, and we see them in other galaxies. And I will show you a very short movie of this accretion process. So the material from the companion stars goes into an accretion disk. The center of the disk is very hot and shines in X-rays, and you might have a jet, you might have a wind, and all of these will produce quite interesting phenomena. So stop this, and we'll show you an example of galaxies. These are outside galaxies, not our own Milky Way. We can see them with Chandra in great detail. This is a system, it's called the Antennae Galaxies. It has a funny shape. It's about 60 million light years away from us. And this is like 30,000 light years across. This is a visual light image from an optical telescope. And this is the X-ray that you see with Chandra, which unfortunately, again, you cannot see the spectacular loops of hot gas that are around this system, are fainter. But you also see a lot of these very bright spots, and those are those binary systems with neutron stars and black holes. Here is a Hubble image of the same system, higher resolution. And here's a little movie that will show you those binary systems varying. And this is important because it really tells you that they're very, very small. So there could well be a neutron star, or most likely a black hole, because they're very, very luminous in the antennae system. This movie shows a simulation of how this galaxy came about. Basically, it's a result of a collision of two galaxies, maybe like our own Milky Way. When this collision happens, the gaseous medium in the two original systems gets compressed. So you have lots of new stars forming, going supernova, and warming up the gas in between them. So what you end up with are those binary X-ray sources, but also a very luminous, hot interstellar medium, as we see in the X-ray image. And this medium isn't just there and hot, but it's also enriched in elements. And with our own, with satellite, with Chandra, these are the Antennae galaxies. This is the hot gas distribution. You see in red iron, you see in green magnesium, and you see in blue silicon. This is the results of stellar evolution, of supernovae explosion. These are the material that, in a way, are the origin of life. We're made of this stuff. Our Earth is made of this stuff. Okay, let's move on. Supermassive nuclear black holes. Black holes, you can see them as a result of a stellar evolution in these binary X-ray sources. But as was discussed also this morning, you can find very large black holes, 100 million, 1,000 million times the mass of our own sun at the center of nuclei of galaxies. And again, this is a beautiful image which you can't quite see, but this is the center of the Milky Way, and this is where...
Perhaps the connection here?
I don't know. I think it's just maybe the room is not, I don't know, it's not dark enough.
Where is it being connected?
It's connected here. But that seems to be okay. Okay, this is in focus, but... Well, if anyone is interested, I can do a private show and go fast over the images later, but maybe. Okay. Well, this is another example instead of a supermassive black hole at the center of a galaxy, which we call the Centaurus A galaxy, is the closest to us active supermassive black hole. And here's the black hole, and these are jets that we see in the X-rays and then in radio of energy coming out of the black hole. And we also see, which you probably won't see at all here, there is an arc of hot gas where these lines are, which is the remnant, we believe, of a huge explosion from this nucleus happened maybe 10 million years ago. So all this activity can be seen in X-rays with Chandra. We can study it in great detail. We can also see the interaction between the black hole and the galaxy. This is an image of a galaxy in the Hydra cluster, which is quite far away from us. It's 840 million light years. And it shows, it would show, if you could see it, cavities in the X-rays. So this is hot gas in this galaxy. This is the nucleus. This is black hole. And then you see these cavities. And these cavities...
Shall we check with this guy?
Yes. Okay. No, go ahead, if you can make it. Right. We were here. Okay, well, I don't know. This is unfortunate. Maybe they'll fix it. So the point I wanted to make here is that there are these cavities we see in the X-rays. And here you see the beginning. But basically, there are two holes in a very bright X-ray source, which is gas at 10 million degrees or thereabout. And this galaxy has a very brilliant nucleus in X-rays, which is the black hole. And the reason there are these cavities is because the black hole has these jets, okay, of very energetic particles that move out the gas in the galaxy. So they fill these X-ray cavities. So we really see the interaction of the supermassive black hole and the ejection from the supermassive black hole and the galaxy around it. I have another example, which is a cluster of galaxies which is even farther away. It's called the Perseus cluster. And in this cluster, I also shows cavity and also shows some ripples, which people, scientists believe are probably the results of sound waves propagating in this cluster that are excited by the supermassive black hole. So it's like music. It's like this cluster is singing. So this is the image of the visual light. So this is the galaxy, and these are the galaxies in the cluster. And next I will show you the image in the X-rays that we've seen with Chandra. So this is the visual light again. Okay, this is the Chandra image. Okay, here you can see it, the cavities. This is the supermassive black hole at the center. And then you see some ripples, which I'll show you better in another figure. And in fact, what I have here, I don't know if it will come out, is a simulation that shows the center black hole emitting its jets, and then you see kind of a sound wave moving out, and that really looks very much, that model, with what we see in X-rays. This is data that have been sharpened so we can see these ripples, and here would be the black hole, these are the cavities, and these would be sound waves that expand in this cluster. Okay, I have two topics next. Okay, so this is basically the same image that I want to talk about and close with. One is dark matter, and the other one would be dark energy. And with Chandra, we can also say something about these topics. Now, dark matter is something that's is lived with us astronomers, at least for a while. This is Fritz Zwicky, who first in 1933, just studying the motions in a coma cluster of galaxies. The galaxies were going too fast for just being in equilibrium with each other, suggested that there should be lots of dark matter, maybe 5 times more than what we see in stars in the visual. And later on, Vera Rubin in the in 1970s, studying the motions of stars in our own galaxy and the other galaxies, found that, again, that these stars on the outside of the galaxies, they move too fast, showing that there should be some other mass there besides what we see with the optical, with the visual telescopes, the stars that we can see. So again, this was consistent with the presence of this dark matter that would be in much larger amount than the normal matter that we see in stars, which is the matter we're made of. So this was called dark matter. Now, dark matter is also seen in X-rays that this would show you, but it doesn't. This is an image of a galaxy, which is an isolated galaxy. And in X-rays with Chandra, we see a whole lot of X-ray light, a very large X-ray halo around this galaxy, which is hot gas. This is several million degrees hot gas, and the only way to keep this gas there in an isolated system like this is if there is a large amount of dark matter, and so this gas is kept there by the gravity of this unseen dark matter. The presence of dark matter is also seen with, for example, the Hubble telescope. If you have a cluster of galaxies, here's the central galaxy, and there are other chirals in the cluster, and the cluster of galaxies is associated with dark matter, any galaxy that's beyond the cluster, farther away from us than the cluster, will be imaged by a lens of dark matter, gravitational image. And the results of this phenomenon is that the images are stretched out, and you basically see, you would see, but you don't see here, like rings of light in this cluster. So this is called Einstein lensing. And again, it's a way by which people can measure the amount of dark matter in this system, which is always much, much more than the matter you see in stars and gas. Now, what I'm going to show you here, and I hope it comes out, is a peculiar example that was found with Chandra. And it's called the bullet cluster. What happens is that usually if you look at a cluster of galaxies with Chandra, and this would be a visual image of a region of the sky where there are 2 clusters of galaxies. So there are 2 concentrations of galaxies. One would be here and one would be here. And normally you see in X-rays hot gas, huge amount of hot gas, sitting on top of the galaxies. And this hot gas is kept there by the dark matter. And you always see this hot gas going with the clusters of galaxies. In the case of the bullet cluster, the hot gas is not coincident with the dark matter, nor with the galaxies that are like raisins in a pudding of dark matter. It's somewhere in the middle. And I'm going to show you, this is so the visual light image that would show you the two clusters of galaxies. Unfortunately, it doesn't quite show it. And, okay, so the next one. Hello? Okay. No. Okay, here we go. Yeah. So in red, you see the X-rays, and in blue, you see the distribution of dark matter that was measured by those Einstein rings seen in the visual light images. So here are the galaxies, here's the dark matter, same here, but the X-ray, the hot gas we see in X-rays is quite displaced from it. And this is because the dark matter only interacts gravitationally. The gas can be compressed and squashed, and the shape of the gas will be reflecting the interaction of these two clouds, enormous clouds of gas with each other. And a model that explains this data, it's a model that shows the two clusters ramming into each other and basically stripping the cloud of gas and showing a separation between the baryonic matter, the gas, it makes most of the baryonic matter, and the dark matter. And I will show you a movie that shows a simulation of this happening. Okay, so here are the two clouds of the two clusters, the dark matter. The clusters go into each other. Nothing happens to the dark matter, but in red, okay, this is the gas that gets stripped and shaped by the interaction. And this is the kind of phenomenon that you can only see in X-rays by comparing also X-rays and visual light images. So it shows a nice results of using these different NASA observatories. Now, more recent results have to do with dark energy. Dark energy, in this conference there's been quite a bit of discussion of dark energy. Theoretically, there are various interpretations, but observationally, what astronomers see is that there is a discrepancy from the prediction of what people believe from the cosmological models of the universe and what people see. And from the X-rays, what we can do, as I showed you before, is study clusters of galaxies because they shine in X-rays because of these very large hot halos. And you can measure the growth of these clusters by comparing the mass of the halos or clusters that you see at different distance from us, which means at different periods in the history of the universe. And so you have some prediction, and you have your data, and you see what the result is. And the result is that it looks like, because it looks like the mass of these clusters doesn't grow as much as you would expect by the standard theories, and you need an explanation is that dark energy will stop this growth. And okay, so I will show you next a simulation of the universe. What we see here. Okay, I'll show it twice, but this is the Big Bang. The galaxies are formed, they expand, and then the expansion stops, and then accelerate again. Okay, expansion stops because of gravity, but doesn't keep stopping. Then after a while, it's compressed enough that there is this mysterious acceleration. This is what's called dark energy. I mean, there is something that apparently stops the compression of the matter in the universe at a critical point and sends everything accelerating away. If you look at clusters of galaxies, okay, just running it again. Gone. What do we see? Oh, this is terrible. What you see in X-rays, it's a huge cloud of hot gas that would fill all this image if you could see it. And this is 10 million degrees hot gas that sits in this huge amount gravitational potential that's resulting from this dark matter on the cluster. And let's assume that there is another cloud of gas in the vicinity, and because of gravity, this cloud will fall into the cluster. So we have gravity, and that will pull the cloud in. However, if there is a force that will stop this to happen, let's call it dark energy, at a certain point, the cluster is not going to grow anymore. So that's the idea. And that's what's found looking at the data. This is not going to come out. I should probably skip it. I had a beautiful simulation of the evolution of the universe here, formation of galaxies and clusters. It's really spectacular if you can see it, but I don't think you can. No, forget it. It's terrible. I'm sorry. Yeah, forget it. So, next. Okay, so what, no, here. So what astronomers measure is looking at different clusters of galaxies at different times from the Big Bang. The prediction would say that the mass of the cluster, if only gravity is the only force that's present, would grow linearly, say, like this. Instead, what's found is the mass of the clusters in recent time grows less fast than predicted. And this is because of this dark energy stopping material coming in. And so these data are consistent with other observations, with the dimming of supernovae, the comparison of fluctuations in the universe in present times and what comes from the microwave background. All this set of data seems to suggest that there is something in the universe that has to be accounted for, which we could call dark energy or we call lambda, that seems to be there. All right, and so one picture that, again, you can't see of the composition of the universe is that 4% of the matter is normal matter, baryonic matter, the matter that we're made of. 23% is this exotic dark matter that we can see, astronomers can see only because of the effect of gravity. We haven't seen a particle of dark matter. I mean, there are theories, but we don't really know what it is. But we know it's there. And then 73%, the majority of the universe would be due to this dark energy or dark matter and energy in relativity are equivalent, that would consist, 73% of the universe would consist in dark energy, if this picture holds. All right, unfortunately, I mean, I have really beautiful images. If anyone of you wants to see it afterwards, I'll show you them on my laptop. If you want to see more, these are 2 web pages you can go to. They have all the public Chandra images and data. And one thing I want to advertise is also that we have a catalog of sources that we found by, we call it data mining. We detect systematically sources in all the public Chandra data. All the data that's taken with Chandra after a year is public to everybody. And so we have assembled a catalog which is continuously growing. So far it's got about 100,000 sources. And you can go, if you go to this web page, you can download the catalog, and then you can use Google Earth in sky mode to display the catalog and just to look at these X-ray fields, and that's for everybody to use. Okay, so this is what I had. Thank you. I mean, a very dark talk.
So I would encourage people, especially the students.
Yeah, I mean, come here.
I would love to show you the images.
Yeah, it's too bad because I don't know if it's. I don't think it's the laptop. I mean, usually. You think it's probably the projector? Yeah, I mean, I have it on a stick, and we can try loading it in yours, but.
Yeah, so maybe also when the talk is posted on the web, it might come up better. Yeah. Okay, so are there any questions? Okay, Bhaskar.
There's one there.
What about our own galaxy?
Our own Milky Way?
Yeah, Milky Way.
Yeah.
It's closer, so there should be better.
Oh, there is lots of data on the Milky Way. We see supernova remnants. There is a whole series of beautiful supernova remnants images. We see X-ray binaries. We see normal stars. At the beginning, I showed you a regional star formation. Galactic center
What
region.
you showed was some nearby galaxy.
No, first I showed you some data. The supernova remnants are in the Milky Way. The galaxy centers, that was the one we couldn't see at all, was also in the Milky Way. But then you can go to other galaxies, which you can do well with Chandra. You couldn't quite do it that well before Chandra. And you see the same type of sources in all sorts of other galaxies.
Question there.
Yeah.
Like Hubble Deep Field, is there any kind of a deep field image taken by Chandra?
Absolutely. There are Chandra deep fields. They continue to grow. Again, you can find this information on the web pages. And basically, there is no X-ray background. They're all quasars. And there are lots of discoveries of absorbed quasars that shine more in the X-rays than in other wavelengths. And I think we're almost at the threshold of seeing Chandra, I doubt will, well, it can do it in a statistical way, seeing primordial galaxies, original, faraway galaxies.
You talked about the quality of the mirrors right at the beginning.
Sorry?
You talked about the quality of the mirrors in Chandra.
Yes, yes.
Yeah. I was just wondering, what is the surface accuracy that you have on the mirrors?
I'm not sure about the circuit. I mean, you can look it up. It's public.
Does it have to be angstroms, or does it have to be?
Oh yeah, it has to be really, really. I mean, the resolution that we have is less than 1 arcsecond. It's extremely smooth. It's yeah.
This is a general question. I'm a particle physicist. Now, we have a long-term program for 10 years, 20 years, and so on. People from LHC, they want to go to ISR. They have certain ideas about how the subject is evolving over the next 10 years, 20 years. They want to get the same spirit here. What is the program of astronomers over the next 10, 20 years, and so on, putting things together?
In X-rays?
Whole thing together.
Well, in astronomy, X-ray astronomy, we have Chandra, which is absolutely unique from the point of view of images. Yes. And what's next? Well, there was a project that, however, didn't make in the priorities. It was called IXO. Another acronym, was going to be a collaboration with the Europeans, but NASA didn't. We have the decadal reviews every 10 years. The astronomers in the United States get together and they set priorities. And so this project didn't make the priorities, so it's not going to happen for the next 10 years. What's going to happen for the next 10 years, and in fact I think is going to take the entire NASA budget, is the sequel to the Hubble, which, however, will be more of an it's going to be an infrared observatory. It's a very large area. The point is to look at primordial galaxies more. And so that's one thing. Another thing, again, to look at primordial galaxy would be ALMA, which is in the millimeter. And that's, again, it's a worldwide collaboration, includes United States, Europeans, and Japanese, I think, are in that. There is lots of, at least, projects that are in project state to go to large optical visual light telescopes. So there is a motion to go in that direction from various collaborations. For the X-rays, I think there are several ways that the discipline can progress. I personally am very convinced that we need to have high-resolution imaging. I mean, that's what Chandra's shown, is that the sky in the X-rays is very complex. So if we really want to study this phenomena without ambiguity, we need to have the imaging. But that means to make a new type of X-ray optics. Chandra is beautiful, the mirror, but it's heavy. So just to bring it up there, it's not going to happen for a bigger mirror. The other thing with Chandra is that it's a beautiful mirror, and it's a huge satellite, but because the reflection is shallow, you really, the effective area of this mirror is this, which isn't that much if you think in terms of corresponding visual light telescope. So there are lots of technical issues that people are looking at, and maybe the fact that we're kind of stuck for the next 10 years. I mean, stuck, people can think of a smaller satellite, a smaller mission, but in terms of a major facility, we are stuck for the next 10 years, maybe 20, so maybe that's an opportunity to think about new techniques and development.
Agarwal was talking about AstroSat,
Yeah.
larger effective area, which will be better than Chandra.
Yeah, but AstroSat, no, in the Chandra regime, the effective area, in the Chandra wavelengths, the effective area of AstroSat is less than Chandra. Now the campus, I asked him yesterday, it's quite a bit. It's 200 square centimeter, we have 1,000, and XMM has 3,000, so that's less. But also the resolution of AstroSat is similar to that of ROSAT, which is the first image I showed you before. So it's a different thing. What AstroSat will do very, very well is the fact that we'll give you this spectral coverage, basically from optical to hard X-ray. So that's unique because you can study, say, active nuclei or X-ray binaries in this whole regime. You can do physics with that in a different way.
So Chandra remains unbeaten. So
Chandra is going to be unbeaten, I think, at least for the next 20 years. So we hope it keeps working.
I actually have a story to tell. You know, Pepe said that this satellite was initially called AXAF, right? Advanced X-ray Astronomy Facility. Right? The Chandra name came later as a result of this competition. So, you know, one day I got an email or a call from somebody in this AXAF office, a senior public relations guy, who said, you know, you seem to have a computer called Chandra. And it's true, I had a computer called Chandra. He assumed that it was, of course, named for Chandrasekhar. But in fact, I had two computers. One was called Surya and one was called Chandra. Right? Okay. Surya was my #1 computer. So he said, you know, I hate to ask this, but could you by any chance give your Chandra computer a different name? I said, I can do it. I'm not wedded to the name, but why? I like the symmetry, Surya and Chandra. Why do you want me to change the name? And he said, you know, this is very, very secret. Nobody knows. But there is this decision that we are going to call this very successful mission Chandra. And we want a web server to be called chandra.harvard.edu. Right. And my computer was chandra.harvard.edu. They said, you know, can you change the name? And I said, sure, you know, for Chandra or for, you know, for X-ray astronomy, I'll be happy to do it. So I changed it. In fact, I was hardly using that computer. We just switched it off. And then we had Chandra. So other than the insiders, like Pepe, who knew the name of this mission much before everybody else, I was probably one of the only other persons who knew what this was going to be named before it was publicly released, because it's a big secret. And then there's a huge event when they publicly release the name of the satellite. But I had this kind of 3 days or so notice before the thing was unveiled.
Well, that's good.
Oh, no, I just switched it off. No, anyway, it was meant for my postdoc, but things keep moving, and we had already gone to the next generation of computers, so it was just hanging around, but it was still registered, unfortunately. So we had to just pull the plug, and everything was okay. 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 So is there any other question? If not, again, let me encourage people to please come.
Yeah, please come here. I will show you the images.
Because she's got it all on the computer. Maybe you can even, if you've got your drives, just get copies and then you can look at it on your own computer, do whatever. But I mean, it's not just that it is named after Chandra. This is a fantastic mission which has produced the best images ever in X-ray astronomy. And as Pepe says, these kinds of image quality, I mean, that quality is not going to be exceeded for 20 years. This is something special. So don't miss this opportunity.
So our students have pen drives and also a lot of drives.
They have drive, yeah. I hope they have enough drive and the thumb drives as well to come and get copies perhaps from Pepi. Yeah,
I have. Okay, no, I've already copied it. Let me get.
Well, you should check with her. Yeah, come on, you have enough memory. Okay, so let's thank Pepi once again. Lovely talk.